Hi, I'm Steven Nestrova, and I'm here to help you out with the kinetic situation when the rate law is governed by a mechanism in which the second step is the rate determining step. So as an example, we're just imagining that we have a reaction between A and B, so two A molecules combined with the B to make this compound A2B, and we're just saying that the observed rate law is K times A squared times B. And so those are the facts. Now, just as a kind of a check on why we can't have a simple one-step elementary reaction, you know, here's our reaction coordinate diagram, there's the reactants, there's the products. If it were just an elementary reaction, you know, those three things reacting to form that, well, the predicted rate law would be K times A squared times B, which does match our observed rate law, but the problem is that that would be an ternary elementary reaction, which we don't allow. So let's go for a two-step reaction, and we're just going to explore what happens when the second step is the rate determining step, as you see here. And here's the stoichiometry of our two steps. I'm saying that two A molecules in a bimolecular reaction react to form this new molecule called A2. And so that's this first step here. A2 appears right there. And I've drawn it as a fast equilibrium, you know, because the activation energy on that step is small. So this reaction goes back and forth pretty quickly. And then the second step, that's the rate determining step. That's where our reaction intermediate A meets up with a B molecule to form our final product here. That's the rate determining step. So our analysis on this will proceed from the observation that the rate of the rate determining step equals K times concentration of A2, this reaction intermediate, times concentration of B. That's all fine. The only problem is that A2 is a reaction intermediate, and so we don't know how to write down that in terms of our reagents A and B. So we can't compare this prediction to the observed rate law, at least not yet. But we can if we take advantage of what we know about that fast equilibrium. So let's step through that a little bit. And so here we have our fast equilibrium, bimolecular in the forward direction, unimolecular in the reverse direction. So if you want to just pause the video and see if you can write down the rate law for the forward reaction and the reverse reaction. Okay, I think this is what we want to write. The forward reaction, it's bimolecular in A, so that would be concentration of A squared, and I'll put in a prime about that. And then now for the reverse reaction, that's unimolecular in the reverse direction. And so I'll just say that's K double prime times concentration of A2. Okay, unimolecular in that direction. How does that help us? Well, the idea is that this is a fast equilibrium. Therefore, the rate at which A2 gets made equals the rate at which A2 falls apart and goes back to our original reagents. That means this quantity here must be equal to that quantity there. So the next step in this analysis, if you want to give it a shot, is to say that's equal to that and then solve for the concentration of A2, since that's what it's going to appear in our rate determining step. Okay, well, here's what I think we should do. I see that K double prime A2 is equal to K prime A squared, so I'll equate those and divide both sides by K double prime, and that means that concentration of A2 must be equal to K prime over K double prime times the concentration of A squared. Okay. So now we have our concentration of our reaction intermediate, and we can put that right into that expression right there. Okay. And let's just see what we get. So the rate law of the rate determining step becomes K. Now A2, I'm going to use this expression right here. That looks like K prime over K double prime, concentration of A squared. That's that expression there. That takes care of that term, and now we still have a B guy right there. Okay, so as long as I get to consider this, you know, set of constants, one new constant, I have a rate law which is second order in A, first order in B. And that's exactly what our observed rate law is. Second order in A, first order in B. So what we say then is this two-step mechanism in which the second step is rate limiting, predicts a rate law that's consistent with the facts. Now, we haven't tested one more thing for plausibility, but that's pretty straightforward, I think. We need to make sure that the overall the net stoichiometry of our mechanism fits with this. But I see I've got two A's there, that's good. Produces an A2, but we gobble up the A2, and so we have two A's plus a B, that's good. Produces the one thing that's on the right, which is A2B. So the stoichiometry works out and the kinetics works out, and so we say this is a plausible mechanism. Okay.